physicist in 2023 published a paper saying the universe might be a giant optimized program. A 2025 paper did the math and showed it would need more energy than every star in every galaxy combined. Both are serious. Both cannot be entirely right. So who's correct? Does physics prove we're in a simulation or disprove it? The answer is not a clean yes or no. It's a chain of arguments that turns the whole question into something deeper. Today we're walking through the actual papers. No Elon Musk. No base reality tweets. Just the real physics arguments. What they get right and where they hit impossible walls. First, let's define the thing. The simulation hypothesis is the idea that our reality is a computer program run by a more advanced civilization. Philosopher Nick Bostrom formalized it in 2003. Musk popularized it. Now it's a meme. But here's the twist. Physicists are actually publishing on this in peer-reviewed journals with equations, not tweets. We're looking at two recent papers that tried to make the hypothesis rigorous. The first one dropped in October 2023. Melvin Vopson, AIP Advances. He proposed something called the second law of infodynamics. Sounds fancy. It's not. Here's the idea. The information content of physical systems tends toward a minimum. Nature seems to delete unnecessary data, like a programmer optimizing code to reduce computational load. Think of a video game. A good developer doesn't render every leaf on every tree at full resolution if nobody's looking. They simplify, they compress, they cut corners. Vopson looked at physical laws and saw the same pattern. Symmetries in particle physics, genetic code efficiency, even the way entropy behaves in certain systems. All of it looks like nature is on a data diet, constantly trimming the fat. And here's the leap. If the universe minimizes information like a coder trimming a bloated script, maybe that's because it is a script. Maybe we're living in an optimized simulation, and the second law of infodynamics is the signature. It's a neat analogy. Nature acts like it's running on a budget server, and Vopson published it. Peer-reviewed, real journal, real DOI, not a Reddit thread. But hold on. There are at least two problems with that interpretation. First, the second law of infodynamics is a novel proposal from one author. It's not a confirmed law of nature. No independent replication yet. No textbook is getting rewritten tomorrow. Second, nature might minimize information on its own, without a programmer. Entropy and information are deeply linked. Shannon entropy, von Neumann entropy, these are standard physics tools. The fact that information decreases, in some systems, could just be ordinary thermodynamics wearing a new hat. It's like looking at a toaster and saying, this toaster minimizes bread entropy, therefore it was designed by a cosmic chef. Maybe, or maybe physics just does that. The simulation interpretation is just that, an interpretation, not a proof. Vopson's idea is provocative, a genuine maybe, but far from a smoking gun. But someone else did a completely different analysis. And it gets worse for the simulation idea. A 2025 paper in Frontiers in Physics took a different approach. Instead of looking for signatures, it asked a brutally practical question. What would it actually take to simulate our universe? Not philosophically, computationally. The authors ran the numbers, and the numbers are not friendly. Here's the problem. To reproduce observed phenomena, a simulation needs a minimum spatial resolution. You can't just pixelate reality at the scale of a grain of sand and call it a day. You need to go much smaller. Quantum mechanics demands detail near the Planck scale. That's 10 to the minus 35 meters. A billionth of a billionth of a billionth of a proton's width. If the simulation cuts corners there, we'd notice. Our experiments would glitch. So the simulation must track an absurd number of bits. Every point in space, every particle, every interaction. And here's where thermodynamics enters the chat. Landwehr's principle says that processing information costs energy. Specifically, erasing one bit of information releases a tiny amount of heat. KT ln2. Tiny, yes, but not zero. Now multiply that tiny energy cost by the number of bits needed to simulate the entire observable universe. Every star, every planet, every neuron in your head, every toaster in every kitchen ever. The total energy required exceeds the total energy budget of the observable universe. By a lot. The graph looks like a joke. The required energy dwarfs the total energy in the observable universe. It's like powering a star with a battery. The numbers are absurd. So that's it, right? Simulation dead. Pack it up. Go home. But no, here's the catch. The 2025 paper assumes the simulator runs on the same thermodynamics we know, the same Landor limit, the same energy constraints. But a truly advanced civilization might use physics we can't even imagine. Maybe they have infinite energy. Maybe they cheat. Maybe they don't use bits. Maybe their computers run on something that makes our laws of physics look like cave drawings. The paper doesn't disprove the simulation. It disproves a simulation built with our rules. And that's a very different thing. Both papers share this flaw. They project our limits onto a hypothetical supercivilization. Vopson assumes a simulator that optimizes code like a human programmer. The constraints paper assumes a simulator that pays our energy bills. But if the simulators are gods relative to us, they might not care about optimization or thermodynamics. They might have solved these problems a billion years ago. Or they might be running the simulation on a laptop in a universe where energy is free and Landor's principle is a punchline. So where does that leave us? We have a rigorous maybe. Vopson's infodynamics is a hint, not proof. The constraints paper is a limit, not a disproof. Both sharpen the question, but can't answer it. The simulation hypothesis remains scientifically unfalsified, but also not actively verified. It's in a weird limbo. Not pseudoscience, not normal science either. It's a hypothesis that forces us to define what reality even means once you bring equations into the picture. And that's the real value. These papers don't tell us if we're in a simulation. They tell us what a simulation signature might look like, and what a simulation would cost. They move the debate from philosophy to quantitative physics. The question is now, can we design an experiment that distinguishes a simulated universe from a base reality? Something beyond our current physics. We don't have that experiment yet. Until we do, the hypothesis is a mirror. It reflects our assumptions about computation, information, and reality. We can't even prove our toaster isn't simulating us. It just sits there, minimizing bread entropy, looking suspicious. So what have we learned? 2 real physics papers. One finds a possible optimization sign in nature's deepest laws. The other does the math and concludes the required computer would break all known energy limits. Neither is airtight. Both expose hidden assumptions. The simulation hypothesis is not dead. It's not proven, it's a structured maybe. And now you have the actual arguments instead of just a tweet. The question is open, but at least now it's a physics question, not just a meme.